going to have homework problems where you have to use this.
Makes no sense.
Okay, so the next thing is really the main thing for this section, and it's Boolean force. This is what the lab's going to be on. Now, I've done a lot of work because I didn't know it would take me most of the period to go over the homework. I've done a lot of work here to try to show you where these equations come from. It's really not that important. So these derivations, I'm going to show you some of it, but don't write it down. Okay? All right. So Pascal not only figured out Pascal's principle, but he also found that the pressure exerted by a fluid depends only on the depth of the fluid. Right? So if you're swimming to the bottom of the pool, the pressure you feel on you has only to do with how deep you are. Below the surface of the fluid, the water in that case, right? That's all that matters. Doesn't matter if you lay down, if you stand up, whatever. All that matters is how deep your head is. Same thing with a cat strapped to the bottom of the pool. Right? The pressure on the cat, that was actually a sophomore physics problem on an exam that I had in college at Texas A&M. On the cat exam. A cat is strapped to the bottom of a pool 10 meters deep. What's the pressure on the cat? And all the problems were like that. It was hard to keep a straight face. But like I said, I'm scarred for life. Okay, so let me give you the bottom line, and then I'll just show you the rest of the stuff. Okay, this is the bottom line. The pressure exerted by the fluid is equal to rho GH. Pressure exerted by a fluid is equal to rho GH. Rho is the density of the fluid. G is 9.8. And H is the height of the fluid, which is essentially the depth, how far you are beneath the surface of the water in most cases in this class. So D is like depth. So pressure is rho GH, and Pascal's the guy who figured this out. So rho's a constant, it's the density of the fluid. G's a constant, it's 9.8. The only thing the pressure depends on is how deep you are below the surface of the fluid, usually water in this case. That's the bottom line. That's what you need to know. Okay? The rest of this stuff is showing you how he came up with that. Yes?
So given density 9.8 and the depth of the object, we can find the pressure exerted on an object.
Yep. So that's the answer to the cat 10 meters deep in the swimming pool problem, right? All you have to do is plug into this equation. Now, there is one thing I should write, just because you need to know this. The density of water is 1 gram per centimeters cubed. And you actually probably won't use that form of it much. It's also 1,000 kilograms per meter cubed. You can convince yourselves of that if you like, or you can take my word for it. Those are the same numbers, just converted with converted units. Yes?
We need to memorize this for a test, or will it be provided?
Can't remember. I'll give it to you on the test if you can't remember it. But it's a good thing to know. I mean, how hard is it to memorize 1 or 1,000?
1,000 times.
If it's not on the test and you raise your hand and say, Dr. Marx, I forget this, you told me, you tell me. I'll tell you on the test, okay? All right, so that's what this is if it's something underwater. So what's the answer to the cat problem? So a cat is strapped to the bottom of a swimming pool 10 meters deep. And I might give you dimensions of the swimming pool, all kinds of extraneous information. Does any of that matter?
No.
No.
What's the only thing that matters?
How far?
How deep was he? 10 meters. So what's the pressure on the cat? I want to use that one. That's base SI units, right? 1,000. So it's rho GH, right? Which is 1,000 kilograms per meter cubed
9.8
times 9.8 meters per second squared times 10 meters. And you can convince yourself that that's going to give you newtons per meter squared, but it will. And what's the answer? It's going to be 10,000, 98,000. Did I need to know how big the cat was?
Nope.
Did I need to know the dimensions of the pool?
No.
No. All I need to know is the density of the fluid and how deep they are.
That
Below
was
the,
a
below.
test in college, that question?
Yep. Now, it's one of those things where if you don't know how to do it, it seems really hard. right?
Next to impossible.
If you know how to do it, it's really easy.
College is basically memorization of things.
Okay, so those of you in honors may want to look at where this comes from. This is where it comes from, right? The force, pressure is the force of the fluid, right? Which is the weight of the fluid in a column. Like the force of the atmosphere on me is the weight of a column of air that's directly above me. So I have a surface area. If you like slice this way, that's like a cross-sectional area. That's the area. You take the whole column of air that goes from here up to forever till the atmosphere ends. The whole weight is bearing on me, right? That's an mg. Right? That mg, that force, divided by this area is the pressure of one atmosphere that I'm feeling right now. Does that make sense? And it's the same thing in water. In water, it's the column of water above you divided by this cross-sectional area. Okay? All right. I don't think I need to spend any more time on this. This equation is the main equation. I wrote all this up here to show you where this comes from. But really, this is the bottom line. You need to know and understand this equation. Okay? So to find the pressure of something in water or any other fluid, all you need to know is the density of the fluid and how deep it is. Okay. This is really important because this is the main thing for the lab. So Archimedes was a dude that lived a long time ago, 212 BC, Greek guy, right? You heard of Archimedes? Some of y'all are better at history than physics.
Yeah.
So you've heard of Archimedes?
Yeah.
So he was a smart guy, and this is what he said. So how long ago would that have been? Like 2,200 years ago? He said, an object immersed in a fluid experiences an upward force equal to the weight of displaced fluid. So let's think about this for a second. A battleship is made of steel. It's really heavy. How does it float?
There's air.
Okay, I don't like that answer.
Magic.
I mean, that's kind of right,
Buoyant
but...
They're making a movie about that.
Okay, why?
It's because how big of the mass is the surface of the water is the space is
Okay. So the boat is huge, right? So when the boat sits in the water, it displaces a massive amount of water, right? And the buoyant force is the volume of the displaced water. So the bigger something is, the more water it displaces, right? So that's the upward force on the boat. As long as that force is larger than the weight of the boat, it floats. As long as the buoyant force is greater than the weight of the boat, it'll float, right? Now, did you say that earlier? It's kind of right. What I'm saying, the buoyant force is greater than the weight, is really the same thing as saying the density of the boat is less than the density of the water. Which is another way to say that how it floats, right? If the mass per unit volume of the boat is less than the mass per unit volume of the water, then it floats. It's more, it sinks. That's kind of what I'm saying. Because there's air, so that lowers the mass of this thing, right? Okay, so this buoyant force is a force, so it's in what units? Newtons. And it's equal to rho Vg. Buoyant force of any solid object in a fluid is equal to rho Vg. This is the upward force, right? When you swim, you feel lighter.
Yeah.
That's because of the buoyant force pushing up on you, because of the fluid you're in. Now let's talk about what this means, because this is really important for your lab. So the buoyant force is equal to rho. Rho is the density of the fluid. How do you spell rho? R-O-W? I actually think it's R-H-O. R-H-O. So this, remember we have something in the water, so don't make the mistake of thinking this density is of the solid thing in the water. This is the density of the water. It's that. Density of the fluid. In every case in this class it's going to be water. So it's that number. V is the volume of fluid displaced by the object. So if the object is completely submerged, what's the volume of fluid displaced?
The whole entire.
It's equal to the volume of the object, right? If the object is 50% submerged,
half the
It's-
volume.
Then the
Half the
volume of
volume.
fluid displaced is half the volume of the object, right? Okay, this is the volume of the fluid displaced, and then G is 9.8. Okay? Okay, so we got this equation in the homework, this equation in the homework, and this equation in the homework. Now I can't remember if this one's in the homework, but it's definitely in the lab. So, if you're in the water and you're swimming, you feel lighter than you do if you're not in the water, right? Okay, so there's something called apparent weight. That if an object's in a fluid, it seems like it weighs less. Okay, and apparent weight is equal to the actual weight of the object, mg, if it weren't in the fluid, minus the buoyant force, which is what's the force pushing up on it because it's in the water. Okay? This is really simple. So we know now that there's this buoyant force that's pushing up on an object in a fluid. So the apparent weight on the object in the fluid is equal to its actual weight minus the buoyant force. That's how much it feels like you weigh when you're in the water. Now here's one more thing that's a little tricky for the lab. If you're floating, or if something is floating in water or in fluid, the apparent weight should be 0. Okay? Now you're going to do calculations on your lab to that effect, and you probably won't get exactly 0, but you should get something close to 0. Okay? Okay. Now I have one last thing, and this is a minor thing, but it's on the test, so I need to tell it to you. Okay? This won't be on the lab, but it's on the test. Bernoulli's principle. I'm not going to focus on it, but you need to know what it is. As the velocity of a fluid increases, the pressure it exerts decreases. That's Bernoulli's principle. So on an airplane, how do they know the airspeed? They have a little tube that sticks out. Look for it next time you fly. There's a little tube that sticks out the front of the airplane. And as the airplane's flying, they're measuring the pressure change in the tube, which is proportional to the speed of the air that's going across the front of the tube. That's Bernoulli's principle. So, as the velocity of a fluid increases, the pressure it exerts decreases. So, the plane has a little tube sticking out. When it's flying, the airspeed is how fast it's going relative to the air. So the air is going by this tube, and the pressure inside the tube is changing because of this. And they're measuring the pressure change, and that tells them how fast the plane is going. In a more mundane example, who has a fireplace?
Oh.
You ever sit by your fireplace on a windy day? What happens? As the speed of the wind, air changes across the top of the fireplace. What happens?
You can hear it.
The pressure in the chimney changes, right? That's Bernoulli's principle. Hmm? Yeah, if you change the diameter. So here's a drawing. This is a pipe that's getting smaller. So the velocity of the fluid going through the pipe is lower here because it's bigger, right? So the pressure is larger. These things are inversely proportional. The velocity is smaller, so the pressure is larger. Here, because I'm cramming it all into a smaller pipe, the velocity gets much faster, and the pressure has to drop. Because that's what this says.
Dr. Marx,
Yes.
so don't you think because it's in a smaller area, the pressure would be more?
Bernoulli's principle. Maybe it doesn't make common sense, but it's true. Okay, I spent this example is in the book, and I just want to talk to it for 2 minutes before we leave. I still have 2 minutes. You don't have to write this down, and it's in the book. I want to give you some common sense as to where this comes from. Okay? Can you hang with me for 2 more minutes, Sam? Maybe? It's just conceptual, common sense. Okay? So here's a tank of water. Doesn't matter what the dimensions are. Here's a cube. Cube is the same dimensions, right? All 3 dimensions are the same if it's a cube. It's underneath the surface of the water. Now if I think about this, so one facet, the top of the cube is parallel to the surface of the water, and the bottom is also. Okay? So think about this.